When you write software on a single computer, you operate inside an idealized mathematical model. The CPU executes instructions exactly as written. If there is a hardware error, like corrupted memory, the operating system crashes entirely. The failure is total, binary, and predictable. Moving from one local machine to thousands of interconnected servers shatters that model. The physical reality of a modern data center is sprawling, chaotic, and vulnerable. This environment introduces partial failure. In a network of thousands of machines, specific components break, stall, or corrupt data in highly unpredictable ways, while the rest of the broader system attempts to keep running. Transitioning to distributed computing means surrendering the predictability of a single processor to the non-deterministic laws of physics. Engineers have two main strategies for dealing with hardware limits. In high-performance computing, used for weather simulations or molecular dynamics, the state of the workload is frequently checkpointed. If one node fails, the entire cluster halts, the hardware is replaced, and the job restarts from the last save. Cloud architecture takes the exact opposite approach. Built on multi-tenant commodity hardware, cloud platforms expect parts to break constantly. The infrastructure is designed to isolate burning racks and automatically route traffic to healthy servers without stopping the service. Global, internet-scale applications demand this continuous availability. You cannot take a massive database offline globally just because one physical server in one data center experienced a short circuit. Because we cannot purchase perfect hardware, the core task of modern software engineering is building mathematically reliable systems out of physically unreliable components. Modern distributed databases are typically shared-nothing systems. The individual machines share no disk and no memory. Their only method of coordination is sending messages across asynchronous packet networks. This diagram shows the blind spot inherent in network communication. When a client sends a request over the network, three things can go wrong. The initial request is lost, the receiving node crashes mid-process, or the final response is dropped on the way back. To the sender, all three outcomes are identical. It only knows that it has not received a reply. The only available recourse is to set a timeout, giving up after a certain number of milliseconds. But determining the exact length of that timeout requires predicting the physical bottlenecks of the hardware routing those packets. This diagram maps network congestion. If multiple machines send data to the same destination simultaneously, the physical switch must line those packets up in an output queue and feed them into the destination link one by one. When that queue overflows, packets are dropped. TCP flow control kicks in, forcing the sender to throttle its rate and retransmit the missing data. The underlying hardware is perfectly healthy, but the network suffers massive latency spikes. Legacy circuit switch telephone networks avoided this by allocating a static, dedicated bandwidth reservation for every call, guaranteeing a bounded delay at the cost of vast inefficiencies. Internet protocol networks share bandwidth dynamically to maximize throughput. This burst-optimized architecture creates mathematically unbounded delays. When a timeout occurs, it never definitively proves a node has died. It only proves the network has slowed down. Time tracking inside these machines is divided into two distinct models. Monotonic clocks measure relative duration, how much time has passed between two events, making them reliable for calculating network timeouts. Time-of-day clocks map to the actual calendar time. The time of day is maintained by physical quartz crystals mounted directly on the motherboard. Because they vibrate physically, their frequency drifts based on the exact temperature of the server rack. Network Time Protocol attempts to correct this drift by pinging centralized time servers, but those NTP queries travel over the same congested IP networks we just examined, inheriting the exact same unbounded packet delays and reducing their precision. This timeline illustrates the danger of relying on those clocks for conflict resolution. Client A writes an update to Node 1. A moment later, Client B writes a newer update to Node 3. Node 1 has a quartz clock that is running slightly fast. It stamps Client A's older update with a timestamp that technically occurs in the future. Causality is inverted. When Node 2 receives both writes, it applies a rule called last write wins. It accepts the older data because of the skewed timestamp, permanently deleting Client B's actual recent update without triggering an error. Systems like Google Spanner navigate this by using the TrueTime API. Instead of pretending a clock is accurate, it returns a confidence interval, an earliest possible time and a latest possible time. In a distributed environment, a timestamp is never a precise point in reality. It is merely an interval of uncertainty. Even with instant network delivery and atomic clocks, the timeline of a distributed system remains fragmented. A process cannot even trust its own local execution speed. Operating systems routinely pause a running thread without warning. The code is suspended mid-instruction, frozen entirely while the rest of the world moves on. These pauses are triggered by routine maintenance. A language runtime stops all threads for garbage collection. A hypervisor will steal CPU cycles to run a neighboring virtual machine. Synchronous disk access or memory page faults will force the processor to wait. The aerospace and robotics industries bypass this by using hard real-time operating systems. These strictly schedule CPU allocation to ensure execution deadlines are met without exception. But an RTOS achieves this by drastically limiting resource utilization. Applying that strictness to multi-tenant web servers is entirely incompatible with the economics of cloud computing. Because web servers operate with real-time guarantees, a single node must assume its threads can be suspended for an arbitrary length of time, rendering any unverified local state highly dangerous. This establishes a foundational rule of distributed systems. A single node cannot trust its own perception. Objective truth is defined strictly by majority quorum. This schematic tracks a distributed lock. Client 1 acquires a lease to write a file, but suffers a massive pause. The lease expires. The lock service grants the file to Client 2. Client 1 wakes up, trusts its outdated memory, and writes simultaneously with Client 2, corrupting the file. This updated diagram introduces fencing tokens. To prevent corruption, the lock service issues a monotonically increasing token alongside every lease. Now, when the paused Client 1 wakes up and attempts a write with token 33, the storage service checks its records. It already processed token 34 from Client 2, so it rejects the outdated request. Fencing tokens protect against honest nodes trapped by outdated state. If a node suffers from hardware corruption and actively spoofs a token, it creates a Byzantine fault, requiring much heavier cryptographic protocols to resolve. A node's internal belief about its status holds zero weight. In a distributed architecture, truth is established exclusively through external, sequential constraints. Software engineers map these hardware limitations to formalized theoretical abstractions, allowing them to write protocols that survive the physical chaos of the data center. This matrix classifies system environments by timing and node fault assumptions. Timing can be synchronous with bounded delays, partially synchronous with periodic degradation, or asynchronous with zero guarantees. Node failures are categorized as crash stop, assuming permanent death, crash recovery, expecting reboots, or Byzantine, assuming nodes will actively lie. By selecting a specific model, an algorithm proves its correctness by mathematically guaranteeing two properties. Safety properties ensure that an incorrect state, like duplicate fencing tokens, will never occur. Liveness properties guarantee that, despite the delays and the crashes, the system will eventually produce a successful result. Distributed engineering does not succeed by assuming hardware executes flawlessly. It succeeds by anticipating the inevitable failures of physics and mathematically constraining the damage.